Hopefully it doesn't. I think it's working. Okay, so this is continued practice with distance, displacement, speed, and velocity. And so last time I'd asked you to try alpha, beta, gamma. And so let's work this together. You can do this one based on concepts alone, or you can actually use some numbers to get numerical answers. But chances are, if 3 people work it, we're all going to choose a different distance numerically. But since this is a ranking problem, we should, if we all use the same correct physics, we should get the same ranking, okay? And it looks like I tried to give you some tips on how to answer this one. Okay, so in each of the 4 scenarios, John starts in town alpha and ends in beta in all 4 scenarios. One sec. Okay, and so the distance between alpha and beta is twice the distance between beta and gamma, and I noted that already. The road connecting them is a straight path. There's no corners to worry about. That actually changes the physics. We'll get to that in 2-dimension motion. And then we've got John driving 4 different ways, or if you want to make it 4 different people, that's fine. Scenario A, B, C, D is what we'll be ranking. And so we really need to, acknowledge what the distance for all 4 scenarios is, the displacement, and the speed, and the velocity. And so scenario A says John drives half the distance, whatever it is, to beta, so D, at 80 kilometers per hour, and the rest of the way at 20 kilometers per hour. And so whether you choose to do concepts or math, you have to recognize that half the distance, alpha to beta, okay? And so you can think of this as 2 intervals. And so half the distance to beta would just be D. And then the other half would be D. And so they have the same distance. And if we look at, nope, hold on, I was going to speed. Let's do distance first. So what would the distance be from alpha to beta? (2D). Or if you want to put some numbers in there, I usually say make up some nice numbers. And so I like multiples of 5, but you can kind of use the numbers given as a guide. So we're given 80 and 20, and then later on 40, 80, 20. And so these intervals at 20, what if you make beta to gamma 20 kilometers, and then this would be 40 kilometers. So that distance would be 40 kilometers. What about the displacement? Anyone? So there's no turnaround, and so the displacement will also equal 40 kilometers. They're the same in this example. And then we're going to need average speed, okay? And so there's a couple ways to do average speed. You can do average speed based on the definition, the defining equation, and it would be a total distance, which we already know, a total time. We don't know total time, but we can easily figure it out since we designated a distance, okay? So if they go 20 kilometers at 80 kilometers per hour, how much of an hour will that first part take?
1/4 of an hour.
Right. So we'd have 1/4 of an hour. Now you might be thinking 15 minutes, but I wouldn't mix the hours that are given in the velocities with minutes. Just go with 1. And then we follow the other 20 kilometers at 20 kilometers per hour. So this one takes
1 hour.
Right, 1 hour. And so we can do the defining equation, and our total distance is 40 kilometers, and our total time would be 1.25 hours. And so if someone will grab a calculator. Now, if you worked this already and you picked a different distance, it's okay. Look at the process that I'm using here. We should end with the same ranking. Anyone get an answer yet?
50 kilometers per hour.
What did it?
32.
Okay, it should come out 32. Do I have a second?
Oh yeah, it's 32.
Okay. And so that one is 32 kilometers per hour. Now there's another method for this same example that we can do to find average speed, and it's that time weighted average. And so that was the piece we started last time. And so the generic equation is V1 times T1 over total time. Remember, it's a kind of a popularity, it's abundance, it's that time ratio factor. And then plus V2 times T2 over total time. And so now we know all that information. We can say 80 times a fourth of an hour, and I'm going to just use decimals here, over 1 1/4, and then V2 is 20 times 1 over 1.25. So someone grab a calculator and work that out for me. And you can do, you know, kind of what we did last time. A fourth of 80 is 20. And then the second part would be 20. Common denominator, we'd end up with 40 over 1.25. And notice it's going to be the same. So our time weighted average should be 32 kilometers per hour as well. And so that's the speed for scenario A, average speed. Now, what about average velocity? Is it 32? Is it 50? Is it different?
It would be 32, I think.
It would also be 32. And really the question is, did it change direction? And so since the distance and displacement are the same, time is the same, time doesn't care about direction, then my speed is going to equal the velocity. So both are going to be that 32. Good deal on scenario A? Okay, I'm going to switch colors for a new scenario. John spends equal time, 50-50. Driving 80 kilometers per hour and 20 kilometers per hour, going alpha to beta. And so if he goes alpha to beta again, then we're going to get the same distance and the same displacement. But what about the average speed and average velocity? Now they're going to be the same again, but do they equal 32? No, if they're equal time 50-50, then these two ratios that we did would be the same, right? And so you can go back through here. You'd have to find the new distance or time. Times are equal. You'd have to do a little bit of math first. Or if they're equal time, I can do the mathematical average and just say 80 plus 20 divided by 2 is what?
50.
Awesome. And so there's the average speed and velocity for scenario B. And then we get to C. C says, John drives 40 kilometers per hour all the way from alpha to beta. And so there's really not a lot of change. And so distance is still going to be 40. Displacement, well, if he starts at alpha and ends at beta, it's going to be 40 as well. What about the average speed? Is it going to equal the average velocity?
Yes, it would.
Yeah, and if you never make any change, then it's just going to be 40. So that one's easy breezy, no calculations. And then D. D has a turnaround. So John drives to gamma 3D, turns back around and goes immediate turnaround. So we don't care about the slowdown and the speed up, and then comes back to beta. That's an extra 20. The whole time driving the same speed, okay? Physics land. So now what's our distance?
80.
80 kilometers. Oops. What about our displacement? Is it 80?
It's still 40.
Good. So again, displacement is final minus initial. And so it's still beta minus alpha. In all scenarios, they started at alpha, ended at beta. So that, you know, that extra 20 to gamma actually gets subtracted when you come back to beta. And so it's still 40. Speed does not care about the turnaround. And I'm going 80 the whole time. And so 80. But since the turnaround, your velocity is not going to equal the speed. And so we actually need to find the velocity and its displacement over time. We know the displacement is 40, but this total time we don't know. But we do know the displacement and the speed, because time is the one thing that's exactly the same for speed and velocity. And so I can use the speed as distance over time. 80 equals 80. So total time would be 1 hour here. And so 1 hour, our velocity is 40 kilometers per hour. So those are different. And now that we have all that, you can actually do your ranking. So the greatest distance is going to be D is greater than, and distance was equal in all the others. So we like to put alphabetical order for the equalities. So most of our keys will be written equalities in alphabetical. Displacement, I had 40, 40, 40, 40, all the same. So you can write that, or you can show they're all equal. Average speed, I had 32, 50, 40, and 80. And so D is greater than B, is greater than C, greater than A. And average velocity, we had 32, we had 50, we had 40, and we had 40. So it'd be B is greater than, C is equal to D, greater than A. All right, questions on the 4 scenarios of alpha, beta, gamma? Okay, and we only had to do that, or we could do that time-weighted average in that first part, okay? All right, the next one I want to go through, let's see if we finish Lisa. We did not, so I hope I told you to go try it and then check the key. I don't know if you did or not. Sometimes students don't always do that. And so let's finish working this one together, and then I'll open it up for any questions you have, okay? And so Lisa, we said there's 5 intervals. We were given a variety of information on those 5 intervals. We solved for her stopping distance for interval 2. And then now we're going to find how long did it take. Now, how long is the driveway? That's a distance reference. But how long did it take? Can anyone tell me what we're going to solve for in part B?
For a time.
Time. So we want to know time that it took to reach max speed once the light turned green. And so if we look up at our vector representation, the light turned green and she sped up to reach that max speed. And I'm looking at interval 4. So I'm going to switch back to green here so it correlates. Interval 4. And so we said we're looking for time. What do we know about interval 4? So a lot of students tell me, I don't know where to start. I see all this. I think I know what to do, but I don't know where to start. Writing out your given is a very handy place to start, okay? And so if I look back at interval 4, we started at 0. We sped up to that top speed. Yeah, it's not the biggest number, but at that scenario, she reaches that max speed. And then what else do we know? They told us it takes 48 meters. And just to remind you, Lisa always went to what I called the right. She always went the same direction. So let's just say she went in the positive. And I didn't define that earlier, so maybe I do now. And so that displacement, you could also call it D, 48 meters. And we're looking for time. And so after you write your given and you identify what you're solving for, the unknown, look for an equation that might involve those variables. And hopefully you recognize it's going to be the same equation. Using that since section 4 had another uniformly speeding up, a uniform change in the speed. That's what allows us to use that mathematical average on the left and the defining equation on the right. And so I'm going to use the same equation, but different plug-in. And so now 0 plus 16 divided by 2. And you can go ahead and reduce that. And then the displacement, 48 meters, and 8 is meters per second. That would be the average speed, divided by this time of the 4th interval. And if I didn't say it last time, we use a lot of subscripts. Some are predictable, like the initial and final. But my 1, 2, 3, 4, 5 are referring back to what I called intervals or sections of the motion. If you like A, B, C, D, E, go for that. Some are flexible. And so now to solve, if you look at it, hopefully you see proportion format. What's best for most is to say, well, cross multiply. You can actually switch the diagonals and it be the same. And to solve for time, you need to divide. And so 48 meters over 8 meters per second. And it doesn't really look like it here, but meters will end up canceling out. Because if you do unit analysis, when you divide by meters per second, you multiply by seconds per meter. So meters would cancel out. And we get 6 seconds. And then C. C is going to be like 4 calculations till we get that answer, okay? And a lot of students are like, oh no, is the quiz going to be all like C? No, you'll have some A and B that are, just using defining equations. But on a normal AP test or quiz that we might give, expect 1 or 2 that are more lengthy in solving, okay? Or multi-thought. You have to use multiple concepts to figure it out. One thought leads to another, okay? In the springtime, maybe we'll start practicing paragraph responses. write out responses for the AP exam. One of the free response will be a multi-step thought or calculation. And so we got to be ready for those. And so how long was she sitting at the light? Well, sitting at the light, I had that as dark blue. So I'll switch over there. And so that's the wait time. You don't go anywhere. You don't move. You cover no distance. I cannot use the average velocity or speed equation. So how am I going to find that time of the third interval? Well, time is scalar. Time for each segment will add together to make the total time. Now, what I'm about to write, a lot of students don't write because they do it in their head. I'm going to show my complete work. That way, if you ever look back at it, hopefully you can follow along. And so we know time of the first interval plus second plus third, and that's what we're looking for, plus the speed up plus the constant equals that total time. Put in what we know. Previous, they told us the whole thing takes 5 minutes because she barely makes it on time, right? Tardy bell's ringing. But I don't want minutes because some of the other times, like the one we just found, is in seconds. So if we didn't do it already, we did. We're going to use 300 seconds for the total. T5, they did not give it to me, and I'll go on and let you know we're going to have to solve for that. And so for right now, I'm just going to put T5. T4, we just found to be 6 seconds. T3 we don't know, and that's going to be our final answer. T2, they said we slowed to a stop in 5 seconds. And then T1 said 2 minutes. We like seconds, so 120 seconds. And so at this point, a lot of students are like, but I have 2 unknowns. This is impossible. They did not give me enough. Pause, and let's see. Can we go solve for T5? So I'm going to, next step, what do we know about 5? Well, for the 5th interval, they told me the velocity was 16 meters per second. That was the top speed, max speed of the 4th interval, and then she maintained that speed. So that means she's not pushing on the gas, not pushing on the brakes, and I guess when she gets to school, she just rolls out of the door, right? Hollywood. So it's a constant. And we're looking for the time. Okay. They did not give me the distance. And if I'm going to do V equals displacement of the 5th divided by the 5th, right? Same subscripts, I need that displacement. It wasn't given. So maybe we pause again. How are we going to find that 5th displacement? Well, we know some of the individual displacements, and they told me the total displacement, and she never changes direction, so maybe all the individual distances add to the total. So just like we did with time, I can say distance or displacement. By the way, if you used D, it's correct on this one. It's the same. And plus the displacement of the 2nd, plus the displacement of the 3rd, I'll come back to that one, plus the displacement of the 4th and 5th, and it equals the grand total. And so we start plugging in what we know. Well, the total was told to us as 4,000 meters. And we're only doing this because we're trying to find that 5th distance. Do we know the 4th? I'm going to scroll back up. I think we do. In the 4th interval, they said 48 meters. In the 3rd interval, the car was stopped. I don't cover any distance. So what I'm about to show you, you'll see all year long. It's called zero out. Physics types, even textbooks, you'll see this. Yes, I can write a 0. And I'm going to do it both ways today. So you can do this. Or if it wasn't a numerical based type of problem, you would just diagonal arrow to the 0. So the third displacement is going to 0 out. And then the second displacement, I think we found that in part A, 45 meters. And the first, it says in our picture, we knew the velocity and it was constant, and we knew the time. We weren't given a distance, but again, so this is a quick pause. And so for the first interval, we know the velocity was 18, and it's equal to that displacement in the first divided by time of the first. So 18 equals displacement over 120 seconds. So to isolate distance 1, I need to multiply both sides by 120. And someone with a calculator, double check this, I'm going off memory here. I think whenever you calculate it, you get 2,160 meters. And so now we can work our way back up. Okay, we didn't run into any more, two unknown situation, no roadblocks. So this is going there, 2,160. And now the only thing to isolate is that fifth displacement. So to isolate it, you would subtract the left numbers from the 4,000. And I believe, again, someone calculate and correct me if I'm wrong, I think you get 1,747 meters. So now we're working our way back up. And now that I know the distance and velocity for the fifth interval, I can solve for time. So 16 meters per second equals 1,747 meters over that fifth time. Again, look at it as a proportion and cross multiply. And I think we get 109.2 something, something, something seconds. So let's talk about Sig Figs and how many digits do we put in, and is the Canvas quiz going to put it in, count it wrong if we put it into the wrong decimal place? So normally we consider 2 or 3 Sig Figs. And so it's really the spirit of it. An AP exam does the same thing. And so I would probably call this 109 seconds. Now, if you put in 109.2, you should still get it right, because we tell Canvas to give you a 2% window range. So 2% above or below. It gives that, it takes care of that rounding issue. Okay? So have no fear. We try to take care of you there. And so now I know T5, I can plug it in up there. So I know 109 seconds. And maybe you've already subtracted the left times from 300, and we get a time 3. Cue the trumpets. Does anyone have an answer?
About a minute.
Right. And so we were in seconds the whole time. You can report your answer in seconds. And I know that you see 60 seconds and you're like, shh, I'm going to say a minute. Maybe the problem didn't specify. Both would be correct. If it said how many minutes was she sitting at the traffic light, you would have to put in minutes. But in this one, it didn't. And so you could actually report either or both if you wanted. So again, is the quiz going to have a problem like that one? Maybe one. And by the way, we don't ever teach directly to any quiz or test, okay? That wouldn't set you up for success come May. And so are you going to have to think about things and use defining equations, maybe do a mathematical average, time-weighted average? Yeah, okay? And so the more variety of practice you have, before a test or quiz, the better. So calm down, it's not all like that one, okay? All right, we got about 20 minutes left. What questions? Do you want to work more? And so the packet, pages 1 through 11 is what, you know, the guide is for the quiz coming up.
Are there any other words that are similar to constant, like the problem we just worked, it said uniformly? Are there any other types of words that mean constant?
So I would say constant, uniform. Another one I've seen is steadily. If the speed steadily. Those are different. And you know, right now I can't think of any others. But yeah, those are all synonymous. They would mean you could do mathematical average. What else? Is there another page? I think we did. We can do the free fall one that I set you up with if you'd like. We can do some of these. We can do, did y'all get the strobe light one? Let's do that one. No one's telling me otherwise. Let's do this one because it's got some technicalities here. And so this is on page 9, I think. It's a strobe photography. This is before slow motion was available. It says in each case, a sphere is moving from left to right. And moral of the story, this direction is always going to be to the right. So let's just call it positive. And it says it's rolling next to a tape that's marked in meters. A flash photograph is taken every second. And the location of the sphere is recorded. The total time intervals shown are not the same for all spheres. And so, you know, how to read these dot diagrams, where's 1 second? Remember, for 1 second to have passed, it has to go from one time to another. And so you can't just look at one ball. This is 1 second. This is the end of the second second. This is 3 seconds. And I'm going to stop there because if you read the question, it says, rank the magnitude, that just means number, of the average velocity for the first 3 seconds. And so in scenario A, we want the average velocity for the whole 3 seconds. So you can ignore whatever comes after 3. It would be the displacement and then divided by 3. So that's one thing they're all going to have in common is the 3 seconds. And so you can see in A, it travels 6 meters in 3 seconds, or it has 2 meters per second. And since those the balls, spheres are evenly spaced, think about your graphing interactive. This is a constant, right? All right, let's do B. B shows it's starting at 0 again, but from ball to ball is a second. So there's 1, 2, 3. And notice the spacing got further. And so since the spacing is getting further, it's traveling faster as time goes on. So this is going to be, it's going to have a change in velocity. Okay. I'm not really saying the A word yet. Okay. So that would be a displacement of 2 over 3 seconds, or, and here's again that rounding, 0.66666 repeating. Where does it stop? Just call it 0.7, especially for this one, because it's just a ranking. We really don't need to do numbers. And let me point that out. I'm going to switch colors just to prove a point. Since you're ranking the average velocity over the same time interval, then if you look at velocity and displacement, Well, it's really whoever travels more displacement has a greater velocity. So these tippers, that's the book these come from, they all like look the same or similar. And so you should be able to answer it just based on displacement alone. You don't have to calculate the numbers, okay? Because they all have the same time. But I already started, so I'll continue. And then C, there's 1 second, 2 second, 3 second. And so the displacement is from final position to initial, and you'll see why I'm doing this in a second. 9 minus 0, that's 9 meters. And then I want to divide by 3 seconds to get the average velocity. So I'd have 3 meters per second. Now these are evenly spaced. This one would be constant. Now I didn't write it, but in scenario B, they are not evenly spaced. So we can just for right now say it's not constant. D, I warned you there was something different about it. Let's talk displacement. Again, final minus initial. So it starts at 1 meter, a little bit of a head start. There's 1 second, 2 second, 3 second. So its final position is 10 minus initial position of 1. So it would be 9 meters for displacement divided by the same 3 seconds. We get 3 meters per second again. Now it doesn't matter to the ranking, but is this one constant like scenario C? Are they evenly spaced? No, they're not. So this one is not constant, okay? And so to do the ranking, again, we didn't have any negative numbers, but if we did, we would then absolute value our answers. So who has the greatest to least? And it looks like that 3 is the greatest, and I've got 2 of them. And so it's not, you know, a set rule, but the way we usually do our keys, if there's an equality, we put it alphabetical order. So I'm going to say C is equal to D greater than A, which is greater than B. Your explanation, I mean, you can use your work to justify, but any time it says explain, I would give one concluding statement. And so I'm going to hit on the concept that I mentioned. And so given equal time intervals, and to make sure you relay, hey, I know what's going on, 0 to 3 seconds. That way your grader knows you know more, you know, than you might write. Given equal time intervals, the greatest average velocity results from the greatest displacement. Okay, and then, you know, C, work above. If you want the grader to look at your work, don't assume they're going to look all over the place for your work. You can tell them, hey, I have evidence right up there. So hopefully that makes more sense. All right. What else?
I have a quick question about the Lance Armstrong question.
Yep.
I still don't know why the final speed is equal to the average velocity.
I don't think it is.
Because like for the first part, you found the average velocity, which was 15, right? And then for the second part, how much did the velocity increase? You set it up so that the average velocity were to be 15, and you set it equal to 10 plus V2 divided by 2.
Okay, so for the final speed, part A, if you will, yeah, I use the mathematical and the definition for average velocity. This is our displacement over time, right? And so I didn't totally write it, but the average velocity for this is 15, right? 150 divided by 10. But for final velocity, I didn't get 15, I got 20. So you said,
Did UI show everything from the TVL and status response?
Can you still explain on the 20?
yes. So I use that combination of mathematical average and the defining equation of displacement over time because it's sped up at a constant rate. Remember, that's kind of the constant, steadily, uniform. So if I put them equal to each other, I plugged in what was given and they gave me the displacement time, they gave me the initial velocity, and then that 2 is just part of the mathematical average. And so once you isolate VF, it should calculate out to 20. So 15 average velocity times 2 is 30. And then you have to subtract.
Everything you see in this table here is coming from TVL.
Yeah, that makes sense.
Okay. But yeah, on that one, they are not the same. What about dropping something out the window? I can work that one.
What's the A word?
Oh, well, can I do it without the A word?
Go for it.
And by the way, there's your A word. You got to have a little fun with it, right? Okay. So I gave you the tip that if you drop something, it actually is released from rest. Okay. And we drop it out the window, it's going to speed up at a constant rate. Ooh, we get to use mathematical average. Okay. The mathematical, yeah, that's what I call it. After going 3 seconds, there's our time. It is then going a final velocity of 30 meters per second. What is the average speed? And so again, get in the habit, if you don't know where to start, list out your given. And so we have VI equal to 0, VF equal to 30, and they give us the time of 3 seconds. Now, average speed, actually at this point, if you recognize mathematical average, you don't need the time. And so we can say 0 plus 30 divided by 2, and that's going to equal 15. A different 15 than before, okay? Just FYI, this is a new problem. And then part B says, how far has the object traveled in 3 seconds? And so this is going to be our defining equation of average velocity, displacement over time. So I know 15 meters per second equals, I'm looking for that displacement or distance, and I know the time is 3 seconds. So to isolate displacement, you need to multiply both sides by 3 seconds, and we get a displacement of 45. And when you multiply meters per second by second, the seconds cancels. So this should come out in meters. Not too bad, right? Got about 5 more minutes if you have questions. And just real quick, so the video that I'm recording doesn't stall too much, just to refresh your memory, I started with the agenda. After today, if you haven't done the practice quiz for the real quiz on Monday, go do the practice quiz Maybe you only did it once and you got some wrong. Maybe you have a submission left. Go try some again. Or if you're like, no, I did it all 3 times, no more submissions, and I got it. Those problems, good, okay? I can do Superman. Well, Superman's probably not on the real quiz, or, you want to practice a variety. And so that's where I would say, go into mastering, sign up. There's an assignment just for extra practice, self-assessment. It'll tell you right or wrong. And sometimes they actually give you hints depending on the question. So that's what you can do to prep for the kinematics quiz. But before next class, try to watch that prep check acceleration. Oh, there's the A word. And there's self-assessment questions to that. And then there's a lab demo. So we filmed a lab of constant acceleration. Okay, and it's gonna say the S word and another A word. Okay. All right, I'm gonna go in and quit recording. I'll stay on a few more minutes.